Hello, my name is Nai Majori, and welcome to Lab 1, Constant Velocity. Alright, so here's just a quick rundown of what I'll be explaining in this lab report. So the main purpose of this lab is to compare the observed position of an object traveling at constant velocity using a software called Tracker to the predicted position or the theoretical position calculated from a computational model called GlowScript. Now for this lab, I will be using a ping pong ball for my object, and hopefully this lab will help demonstrate the principles of Newton's second law. So what even is Newton's second law? Well, Newton's second law states that the net external force equals the change in momentum of a system, and momentum is just mass in motion, so mass times velocity, divided by the time over which it changes. So here's a general formula for that. And if we take it further and derive it, we can get that the final velocity equals the initial velocity plus the net force over mass times the change in time. And this is called the velocity update formula. And what this tells us is that if the net force acting on our system is zero, the velocity does not change. All right, so what did I even do? Well, first up, I recorded a video of the ping pong ball going at constant velocity. Then I uploaded this video into Tracker and tracked the ball's position frame by frame. Next up, I created a computational model of the ball's predicted position in GlowScript. And then I generated a spreadsheet of the observed and predicted positions and graphed this data over time. And finally, I compared both models and made conclusions. All right, so here's just a quick video that I took of the ball going at a constant velocity in my beautiful dorm room. And all those red diamond shapes that you see is me going in, inputting the center of mass at each frame. And you can see that the graph of the position versus time, it appears linear, but we're going to be making a computational model to actually show if it is linear or not. All right, so with the data we collected from the tracker analysis, we can see that the total time it took for the ping pong ball to go from start to finish was about 1.3 seconds. The initial position of the ball was approximately 0.000124 meters in the x direction, and the initial velocity can be calculated by taking the change in position over the change in time of the first two time frames, and this gives us about 0.718 meters per second in the x direction. Now, these three data points will be used directly into our computational model. Now for the fun part, altering the code. So first up, I set the net force to 0 since constant velocity means no net force. Then I input the initial velocity and position as obtained from our tracker analysis. Then I set delta t to 1 over 30 since the video was recorded at 30 frames per second. And now the mass of the ball does not affect the velocity since the velocity update formula says that if net force is 0, mass basically just cancels out. And the position formula as seen right here, it's going to be used to predict the location. And since our velocity is constant, we should see a positive slope in our position time graph. All right, so after all those tedious procedures, we're left with this beautiful graph right here. And what this tells us is that as time goes on, well, our experimental position starts to diverge away from the theoretical position. And this means there has to be some outside force that kind of slows down the ping pong ball. All right, so what are some possible errors? First up, we got outside forces. And now's a good time to differentiate between the system and surroundings. The system is what we're studying, in our case, the ping pong ball. And the surroundings is literally everything else. It could even be some random dude up in space. Well, as the ping pong ball is rolling, the surroundings, such as the ground or air molecules, are kind of pushing against it, slowing it down, and that kind of skews with our ideal results. Next up, we got rounding errors, and this can add deviations to precise results. And lastly, position tracking. There were differences in manually placing the center of mass in Tracker. Let's dive a bit deeper into the data with some further questions. First up, what if the positive x and negative x axes were interchanged? Well, honestly, nothing would happen except the slope of our graph would now be negative, but all the physics is going to stay the same. Next, is the net force acting on our ping pong ball actually zero? And if so, how many forces were added together? Well, since the computational model overestimated the position of the ball at greater time intervals, there had to be some other resistive forces at play, such as friction from the ground or the air resistance. And this therefore did not give the system a net force of zero. However, in the y direction, we do have a net force of zero, or else the ball would just skyrocket straight into space or plummet down into the core of Earth, which would be very interesting to see. All right, thank you so much for your attention, and I hope you learned a thing or two from this lab report.